In this lesson, I'm going to show you how to solve various problems involving compounding of interest using exponential functions. What I have here are several scenarios that we're going to look at that are taken directly from the problems in the lesson in Hawks, lesson 5.1. So in this first scenario, we're initially investing $9,300. That's our principal, P. The rate of interest is 7%. The amount of time that we're investing is 24 years, and interest is compounded continuously. So when you're compounding interest a certain number of times per year, n, this is the formula that you use. So we take our interest rate divided by n, and then we multiply by n in the exponent times the amount of time. But this is different. When it's continuous compounding, we use the natural exponential function. So our final value, which I'm denoting by a, is principal P times e to the r times t. It's what you would get if you use this formula and you let n go to infinity, this is the result. So if we go ahead and fill in all the values that were given, so the value is going to be 9,300 times e, it's the base of a natural exponential function, times r, which is 0.07, so it's expressed as a decimal, times 24. So at this point, you need to turn to your calculator to work this out. So I have 0.07, that's a point there, okay, times 24, so it's 1.68, and then plug it into e to the x, and you get value 5.37, etc. Then you multiply that by your principal, 9,300, and what you get is, rounded to the nearest cent, $49,899.67. So that's pretty substantial growth, but we're investing for 24 years. This shows why it's important to start investing for retirement early to give it interest more time to compound. Okay, in this next scenario, we are investing $8,300. That's our principal. And we're going to look at two possibilities here. Either a lower interest rate, only 4%, but compounding daily. The more often you compound, the higher your ending balance will be. Or we can invest at a higher rate of interest, 5%, but compounding less often. So we have a trade-off here. So here we have a lower rate but compounding more often, which helps, or compounding or have a higher rate and compounding less often. So which factor is going to win out here and produce the higher balance? So for the first case, compounding daily, we're going to assume a 365-day year. So we have our principal, and then we use this formula down here with n equal to 365. So I'm going to have for daily 1 plus n, 1 plus r for rate of interest over 365 raised to the 365 t power. So then you go ahead and fill in the numbers. So 8,300 for p, and then 1 plus 0.04 over 365 to the 365, and we're just going to compare these options by, we can pick any value of time really, we'll just pick for convenience 1 year, t equals 1. Okay, so now when I go to my calculator to work that out, I have 0.04 divided by 365, pretty small number there, plus 1. And then I raise that to the 365th power. And what you get is 1.0408, etc., times 8,300, and you get a few $100, $8,638.71. Now, for the other scenario, compounding less often, only once per year, but at 5%. So I will have P A is equal to P times 1 plus R to the T. So it's going to be a little simpler. So we'll have 8,300, 1 plus 0.05. So I can tell already before I even work this out that this is going to be more. Because when I worked out this part, 1 plus 0.04 over 365 to 365, I got 1.0408. Here we're going to have 1.05. So let's go ahead and work it out anyway so you can see the difference. 1.05 times 8,300. So we actually didn't need to do any exponentiation in this case because it's just for 1 year. And we get $8,715 even. So significant, and that difference would only grow but when investing over time. So now if we go with that option, 5% compounding once per year, well, let's see how much we have after 5 years. So we use the same formula, A is P times 1 plus R to the T. So I fill in numbers, 8,300, 1.05 raised to the 5th. 1.05 to the 5th. So use your X to the Y button for this. And then multiply that by 8,300. And you get a gain of a little more than $2,000. So $10,593.14, rounding to the nearest cent. Okay. Now, in the final scenario, we have something quite different here, where we're not given the principal, P. We don't know how much we're investing up front. We just know how much we want to have at the end. So if we're earning 9% interest over a period of 5 years, compounding annually, and we want this amount at the end, how much will have to be invested at the start? So we're going to use the same formula as before. This formula, only working backwards. Okay, so I have A is P times 1 plus R to the T. So now I have this value coming out equal to P, which is unknown in this case. And then I have 1 plus R, which is 0.09 for 9%, raised to the 5th. So I can go ahead and work out this number, 1.09 to the 5th. Okay, and I get 1.539, etc. And the idea is, instead of before, where I would multiply this exponential expression times my principal to get my final value, I'll take my final value and divide it by this amount to get my principal. So I'll go ahead and work it out over here. So I have my P is equal to 141,000 divided by 1.09 raised to the 5th. So this value in the denominator, I've already worked that out on my calculator. So that's what I mentioned earlier, about 1.538 or 539. So now I'll just take 1 over x, and then I'll multiply that by 141,000. Okay, and the result that you get is, rounded to the nearest cent, $91,640.32. Okay, so that amount invested at the start and earning 9% interest over 5 years will get you to $141,000 at the end of 5 years. So when you have to backtrack like this, where you're given the final amount and you need to find the initial amount that will get you there, you work out this exponential part, this 1 plus r over n to the nt, and then you divide your final amount by that instead of multiplying, as we see here. Same thing would be true if this was continuous compounding. I will work out e to the rt and divide my final amount by that to get the initial amount, to get the